Hello friends, welcome to the Convection and Radiation Part 2 under the edges of heat transfer phenomena in polymer process engineering. Now let us have a brief outlook that what we discussed in the previous lecture. We discussed about the conduction in polymeric system with a couple of examples. Then we discussed about the convection in the polymeric system, convection in the laminar flow polymeric system, convection in the laminar flow of the molten polymers. Then we discussed about the heat transfer data of the molten polymers and the soft polymers, then heat transfer in the turbulent flow of polymers. In this particular aspect, we are going to discuss in detail about the convection heat transfer in the laminar flow, convection heat transfer in non-circular conduits. We are going to discuss with the convective heat transfer in the turbulent flow with the certain examples. Then apart from this, we are going to discuss about the heat transfer in the polymeric system, radiation heat transfer in the opaque polymers, radiation in the semi-transparent polymers, and we will discuss some of the example pertaining to the radiation. Now let us talk about the convective heat transfer in laminar flow. So various experimental studies of heat transfer in the flowing polymeric system, this can be broken down into various categories. Especially we are going to discuss the two categories. The first category of the involved experimental measurement of heat transfer in flowing polymer solution. This system combined with the Leibniz approach to yield a Nusselt-Grace correlation. And the second category, this is considered the measurement of temperature profile data for flowing molten or thermally softened polymer system. Now several authors, they have performed experimental and analytical studies in laminar horizontal flow heat transfer in non-Newtonian fluids under the condition of constant heat flux at the wall. They have taken into account the variation in the viscosity with respect to temperature by including a correlation term in the consistency index. So their final correlation, which is represented in this form, you can see that Nusselt number in the laminar flow, this is equation number 1. Now this from this particular equation, some of the co-worker, they modify the first category by doing their experiments, and their findings, they have summarized that if Grace number is greater than 10 and eta is greater than 0.1, then the equation can be modified to this one. This is represented as equation number 2, where Kb and Kw are the power law consistency indexes evaluated at bulk fluid and wall condition, and this is well represented in this particular figure. Now if Grace number is less than 20 and eta dash is less than 0.1, then the equation can be modified like this. We have represented in equation number 3. Delta to the power 1 upon 3 is obtained from the graphs, and Kb and Kw are the power law consistency index and evaluated at the bulk fluid and wall conditions. Now other experimental studies for the polymer solution involves the work of the thermal entry region and a constant wall flux. Some of the workers, they have used the numerical solution of the energy equation to test the experimental data over Grace number, and that ranges from 80 to 1600. Then Joshi and Burglis in 1974, they used a constant wall flux and correlated the power law fluids, the effect of fluid property variation with the temperature. Certain investigators, they found some of the cases that free or natural convection, they occurred in the certain system, and these are generally confined to the low Grace number, that is around 20 region. Now in addition, the ratio of Grashof number to Reynolds number, this is like this, it should be 5 or larger for free convection to be sizable. In such cases, the expression is to be used like this, which is represented as equation number 4, where the Grashof number is defined as per this usual notation, where this epsilon is the thermal expansion, d is the diameter of the tube, mu is the apparent viscosity at wall condition. The earliest experimental studies of heat transfer to the flowing molten or thermally softened polymers, papers of Bayer and Dahl in 1952 and Scott and Kagan in 1964. These dealt mainly with the determining the radial point at which the temperature approximated the mass average fluid temperature. Bird in 1955 measured a few experimental points that did not check well with the theory. Thereafter, some of the co-workers, they also indirectly checked their theory by showing the calculated and experimental average flow rates of thermally softened polymer undergoing heat transfer compared favorably. So, one of the study being carried out independently by Lewin and Grisky and Veitch, this set the stage for a considerable number of experimental measurements. So basically those studies developed the concept of using thermocouple parallel to axial flow and pointing upstream. This is the placement of the thermocouple for the temperature profile measurement. Now in this particular table, there is a comparison of various thermocouple arrangements like thermocouple configuration. Here you see that the thermocouple configuration is given, and the dynamic response and thermal errors and mechanical stability is given. So let us take one example, that is for A, where the dynamic response is very poor and thermal and mechanical stability is also very poor. Now if we take the example of D, where this is the placement, the dynamic response and thermal errors, they are poor, but mechanical stability improved over the different A, B and C. So this is the classical representation of different positioning. When we are talking about the heat transfer in the laminar flow of the molten polymers, so the point covered in this particular table, it should be recognized that the configuration F, this configuration, being parallel to flow and pointed upstream, this will produce the least flow disturbance. So also this configuration F would minimize the shear heating at the thermocouple. So number of investigations being carried out and they made temperature profile measurement of flowing molten or thermally softened polymer system. They used the configuration F. Let us take an example. The number of these studies were directed for measuring temperature in the exit of a screw extruder or within the plunger or injection molding machines. Now these placements, they results a large temperature fluctuations anywhere from 10 to 30 degrees Celsius, and these are the number of possible reasons for this occurrence. So first, both temperature and velocity profile would undergo rearrangement, therefore influencing the reading. Next, although the configuration F, which we discussed earlier, this was used to the thermocouple holder, was quite sizable, this could have caused the flow disturbances and considerable viscous heating, either of which would have influenced the reading. Now here you see that this is the device for measuring the flowing polymer temperature profile. As usual, we are having the extruder, control panel, pressure gauge, safety rupture disc, heating tape and all these things, and a metering pump in oil jacket. So they performed experimentally to find out the things. Now there are various device, average inlet temperature thermocouples, multi-probe profile rings, heat exchanger sections, hot oil circulating units and thermocouple switches. So this device is used to measure the temperature profile, which is represented in this figure. The thermocouple, they are iron constant ton. They enclosed first in the hypodermic tubing and then in a stainless steel shed. Teflon tubing, they are used as an insulation between the tubing and the shed. The construction ensured against the heat conduction error. The outside diameter of each probe was 0.0625 inch, and this means that the given thermocouple surface seen by the flowing polymer was only 0.4% of the total tube cross-sectional area. Now, studies on non-circular conduit cases for the convection heat transfer to and from the polymer system have been quite limited. This team Sukov, they carried out the earlier studies and they involved the taking in the approximate velocity profile, which was found by the Chichester, and then using to solve the energy equation assuming constant physical properties and no viscous dissipation to yield the average temperature and the Nusselt number. Another study, Sukhov and co-worker, they used to exact velocity distribution instead of approximate profile to solve the energy equation. Cozier and co-worker, they used the Levick technique to find appropriate equation for heat transfer. Now, there are several equations developed by Crozier for the non-circular channels. Various equations being developed by the Crozier in 1964. Now, the one equation, that is HADE over K, is equal to 1 by 2 d square Cp Zz gamma B over gamma W to the power 0.14. This is equation number 6. And when the Gray's number is less than 3, and for the Gray's number greater than 20, then the equation becomes HADE over K is equal to 1.86 into d square Zz Cp over Kl over 3 2n plus 1 3n to the power 1 by 3 gamma B over gamma W 0.14. Now, where this HA is the average heat transfer coefficient, DE is the diameter, K is the thermal conductivity, gamma B is the fluid viscosity at the bulk temperature, and gamma W is the viscosity at wall temperature. Now, for the range 20 is greater than, when the Gray's number is between 20 and 3, the work of Teen and Sukov et al. This can be used. In the latter case, the point temperature is given as a function of reduced length for the power law fluid, eta is equal to 1 by 2, where this particular equation can be utilized, and this can be represented mathematically like this. Now, if we use the equation 8, where lambda is the reduced distance, that YB, Y is the vertical distance measured from the center line, and B is the half plate separation, and psi is the reduced length. So, Kx over rho Cpb square Vx maximum, with the x is the axial distance. So, the average number can be represented like equation number 9. The other work, some of the researchers, they performed considered the parallel plates or slits, and all three studies which are listed here, they involved a theoretical solution of the energy equation that included the viscous dissipation, but neither temperature dependent properties nor compressibility cooling. Another co-worker of Lin and Hirsch, they reported the theoretical solution for the heat transfer with flow in an annulus with viscous dissipation and a moving inner cylinder. Now, there appear to be no other heat transfer data available for flowing polymeric system in non-circular cross section. However, the situation can be handled by using the geometrical parameter technique, which was developed by Kojicki in 1966. As per the Kojicki in 1966, the modified Reynolds number is given by 4RH V rho over N, and this is equation number 10, where RH is the hydraulic radius for the conduit, that is the cross-sectional area available for flow-weighted perimeters, and effective is the effective viscosity, which is represented by this, and V is the average velocity, and rho is the density, and A and B are the empirical constants. Now, in other segment, other co-workers, they reposted the Reynolds number value by this equation, that D equivalence V rho over an apparent, and this is represented as equation number 11. Another workers, they rewrite this particular equation or rearrange this equation in this particular form, where D equivalent is represented as equivalent diameter, V is the average velocity, rho is the density, eta k, and they are the power law parameters. Now, this equation 11 can be used either with the expression to give a relation of equivalent diameter, and by putting the value of equation 10 in the equation 11 and 12. So, this can be represented as equivalent diameter 4 RH eta tau wall 2V over RH to the power A plus B. This is equation number 13, or equivalent is equal to 4 RH V to the power A plus B. Now, this is equation number 14. In general, situation in which the polymer turbulent flow are encountered, they are very limited. Usually a slurry equation in the turbulent flow is important, and this is represented as equation number 15 in this aspect. Here the important factor is the K slurry. This is the thermal conductivity of the slurry, and mu is the slurry viscosity, mu L and mu Lw, they are viscosities of the suspending liquid in the bulk and at the wall. So, for slurry viscosity, mu S, this can be given as mu L over 1 minus x nu or x nu B to the power 1.8. This is our equation number 16. So, another relationship, Thomas in 1960 he gave another relationship which is like this: H over CPV, CP K slurry to the power 2 by 3 neta wall over neta apparent to the power 0.14, and which is 0.027 dV rho neta apparent to the power 0.2. Now, this is our equation number 17. Now, in the general relation recommended for the turbulent heat transfer to flowing non-Newtonian is developed by Metzner in 1958, and this was done by the analogy with the momentum transfer. Now, this particular equation includes the constant heat flux, equality of ED thermal and momentum diffusivity at all radius, no dependence of fluid on time, no fluid elasticity, large Prandtl number, the assumption that heat flux is a function of tube radius. So, thus this result can be represented as equation number 18, with the limitation that Prandtl number into Reynolds number square F is greater than 5 lakhs, where F is the friction factor, and no published heat transfer data appeared to be available for turbulent flow of polymeric system through other geometries. Now, let us take a couple of examples. In this particular first question, a polymer solution of where neta is 0.5, K is 90 degree Fahrenheit and 51 pounds viscosity, activation energy of 14,900 BTU per pound mole, is fed into a 1-inch internal diameter stainless steel tube of 10 feet long at a mass flow rate of 750 pounds per hour and a temperature of 90 degree Fahrenheit. The velocity profile is fully developed before the solution enters the heated tube. Heat is supplied by the steam condensing at 20 psia. Remaining fluid properties are density, which is obviously required, which is given, specific heat is given, thermal conductivity is also given. So, you need to calculate the exit temperature of the fluid. The temperature of the condensing steam is given as 227.96 Fahrenheit for the purpose of calculation. Now, I will take is at 228 degree Fahrenheit, and the value of Kb is given 11.182 pounds and Kw is also given. So, putting all values in the equation, so we get H is equal to 0.5 B upon 1 by 12 into 1.75, 125 to the power 1 by 3 into 90 into 11.182, 3.315, 0.14, which is equal to 69.73 BTU. Now, if we take the enthalpy balance, which is WCP delta T, then it comes out to be this mathematical representation T wall minus T fluid, which is average. So, WCP T2 minus T1, which is equal to HA T wall minus T2 minus T1 over 2. So, this comes out to be 750 over into 0.6 into T2 minus 90 Fahrenheit, and this comes out to be 69.73 pi 12 into 10, and this, the calculated value of T2 is 137 degree Celsius, and this is our answer. Now, let us take another example. A flowing polyethylene melt, which is maintained at 300 gram per minute, is being heated in a rectangular duct, which is having the dimension of 1 inch into 2 inch. Now, initial polymer temperature is 410 Fahrenheit and the exit temperature is 425. Determine the wall temperature needed to accomplish this for 10 feet length of duct. It is given that the value of A and B, which is required, it is the value of A and B is given, the CP value is given, W value is given, K is given, tau value and RH and eta apparent and V is also given. So, let us try to solve this particular problem. Now, Nusselt number, the Nusselt number for this case is given by this particular mathematical representation, which is equal to 10. Now, this V is equal to 4H over 2V over RH, which is equal to 4 into 1 by 36, 0.725 over 2.9 into 10 to the power minus 2 over 2 into 5.27 into 10 to the power minus 4 feet per second into 36 feet, and that whole to the power 0.9716, which comes out to be 0.1045 feet. Then H is equal to K over DE, Nusselt number. This is comes out to be 0.148 over 0.1045 into 10, which is comes out to be 14.18 BTU over H 15 degree Fahrenheit. So, once again, WCP T2 minus T1 is equal to HA T wall minus T1 plus T2 over 2. So, if we rearrange the equation, we get WCP over HA into T2 minus T1 plus T1 over 2 plus T2 over 2 is equal to T wall. If we substitute the values in the equation, we get 300 into 60 into 453.6 gram into 0.68 over, this is in gram per minute and minute per hour. Then 1 for 14.8 BTU over HFT square, which we have calculated. Then 2 meter square, which is given, FT square over 144 meter square into 10 FT multiplied by 15 degree Fahrenheit plus 417.5 degree Fahrenheit, which is equal to T wall. So if we solve this, we found it that temperature of the wall is 623.5 degree Fahrenheit. This is our answer. Now let us talk about the radiation heat transfer in the polymeric system. Now the substance can emit the various form of radiant energy such as X-rays, gamma rays, all these things. The only form produced by virtue of the temperature is the thermal radiation. At temperature near or below room temperature, this mode of heat transfer is not at all important. So at a temperature in the range of say 1000 degree Fahrenheit, the radiant thermal energy can be significant. So if the thermal radiation is conceived as a photon gas, it is possible from the thermodynamic to show that the energy density of the radiation is EB is equal to small theta T to the power 4. The J is the Stephen-Boltzmann constant, T is the absolute temperature, EB is the energy emitted from a black body, one in which the absorptivity and emissivity are unity. So the black body represents the idealization that only be closely approximated experimentally. For any other body that is termed as a gray body, the emissivity epsilon, which is represented as epsilon is equal to E over EB, or the ratio of intensity emitted by a body relative to black body. So for all bodies in the radiation equilibrium, alpha is equal to epsilon, where alpha is the fraction of incident radiation absorbed. A very important aspect of radiative heat transfer is the system geometry. This is accounted for by using the radiation shape factor, and also called the view factor, angle factor or configuration factor, and defined as say F12, that is the fraction of energy leaving the surface 1 and reaches to surface 2, and F21, that is a fraction of energy leaving the surface 2 and reaches the surface 1. So ultimately it can be shown by this particular mathematical relation, where phi 1 and phi 2 are the angle between the A1 and A2 respectively, and the normal, and R is the length of the ray joining A and A2, that is the two bodies. Now the radiation shape factor, this can be computed for the different situation and then used with the equation. So it can be represented as Q net is equal to A1 F12 EB1 minus EB2, which is equal to A2 F21 EB1 minus EB2. So Q net has become A1 F12 EB1 1 minus EB2 EB1, which is equal to small then A1 F12 T1 to the power 4 1 minus T2 over T1 to the power 4. Now if T1 is greater than T2, then Q net is equal to small sigma A1 F12 T2 1 to the power 4. Also it is possible to write the Q net expression in the form of Q net is equal to HR A1 T1 minus T2, where HR is the radiative heat transfer coefficient. Now for non-black bodies connected, non-black bodies connected by third surface which is not exchanging the heat, then Q net is equal to small sigma A1 T1 to the power 4 minus T to the T2 to the power 4 over A1 plus A2 minus 2A2 F12 over A2 minus A1 F12 square plus 1 over epsilon 1 minus 1 plus A1 over A2 into 1 over epsilon 2 minus 1, where epsilon 1 and epsilon 2 are the emissivity of surface 1 and 2 respectively. For a special case of infinite parallel planes, Q is equal to small sigma A1 T1 to the power 4 minus T2 to the power 4 over 1 epsilon 1 plus A1 over A2 into 1 over epsilon 2 minus 1. Now let us talk about the radiation heat transfer in opaque polymeric system. In many instances, polymer systems are essentially opaque to thermal radiation. This means that incident radiation absorbed by the body is converted to heat at the surface. Now this surface heat either is lost or flows into the polymer by conduction. So for such cases, the temperature distribution of such a polymer will depend not only on the radiant energy flux but also on the conduction and surface convection behavior. Now, some of the co-worker, they have considered this case for slab constant initial temperature Ti. For such cases, the temperature distribution within the slab can be given by this particular equation, where A is the half thickness of the slab, T is the time, X is the distance from the center line of the slab, and Qs is the heat flux across the surface. Now, this particular equation, this can be rewritten for considering the center line temperature and the surface temperature expression. Now, if the ratio of this Ts minus Ti to Tc minus Ti is taken as I, the uniformity index, then I can be represented like this, and with a certain modification can be represented like this. So, therefore, the uniformity index I can be represented as I is equal to phi alpha T over A square. This relation of I to alpha T over A square can be used to set the slab dimension or required time of heating for a given energy interchange solution. Now, let us take another example of radiation. Now, a 3 feet wide strip of an opaque polymer, which is 0.02 inch thick, is being heated continuously between the banks of infrared heater at 1500 Fahrenheit. Each heater bank has an area of 0.08. If assuming that the heat is transferred entirely by radiation, calculate the net gain in enthalpy of the polymer if the rate remains 25 feet per minute, and we can take the polymer density as 80 pounds per cubic feet, and it is given that small theta is equal to 0.1714 into 10 to the power minus 8, and epsilon is given at emissivity is given as 0.9. Now, this particular equation can be used for with the additional stipulations that the radiant energy absorption by the heating element is negligible and that the temperature of the heating element is much greater than the polymer's temperature. Then this can be written as like this. Now, if you substitute the value, then this can be 0.1714 into 10 to the power minus 8 BTU per into 2 into 0.08, 0.90, that is the emissivity 1960, and which is comes out to be 3650 BTU per hour. Then the mass rate of polymer, which is given as 25 feet per minute into 60 minute per hour, 3 feet, 0.0212 feet, 80 pound per cubic feet, which is equal to 600 pound per hour. And the enthalpy rise is 3650 BTU per hour over 600 pound per hour, which is comes out to be 6.25 BTU. This is the required answer. So dear friends, in this particular segment, we discussed the various aspects of conductive heat transfer. We discussed about the convective heat transfer among the polymeric system. We discussed about the radiative heat transfer. We discussed various correlations, various theories, and all the aspects are being covered over here. So for your convenience, we have enlisted various references you can use as per your requirement. Thank you very much.